Okay, so let us continue the discussion on this Otto cycle analysis, and we have looked at the thermal efficiency and the other things for the ideal cycle, and also talked about when the efficiency actually differs in the real cycle. Now, we are discussing about the mean effective pressure, and then we can do pressure which could be IMEP, that could be defined as WCI by VD, and one can write PI NR by NVD. Now, if brake work is used, then brake mean effective pressure, which is called brake mean effective pressure, which could be written as also like PB NR by NVD. So, both mean effective pressure are related like BMEP equals to eta m into IMEP. So, they are connected with the mechanical efficiency of the shaft turn. Now, also we can define the friction mean effective pressure. So, like FMEP, which is IMEP minus BMEP. So, we have PB equals to 2 pi NT and BMEP is 2 pi TNR by VD. So, with that also we can have some other definition of the thermal efficiency of the Otto cycle. Let us say we can define the thermal efficiency also identified as the fuel conversion efficiency, like then we can write eta TH equals to indicated power by fuel mass flow rate into heating value, which is Pi by m dot F into QHV. So, this is what one can derive, that fuel conversion efficiency. Fuel conversion efficiency. Now, also we have air fuel ratio or fuel air ratio. Now, if you say A by F, that is air fuel ratio. If you say F by A, that is fuel air ratio. Now, for normal operating range, SI engines or the gasoline engines have a air fuel ratio of something around 8. So, the fuel air ratio would be 0.056 to 0.05083, or CI engine, this is typically 18 above to 70, which would be 0.014 to 0.056. Now, also we have specific fuel consumption SFC, which is specific fuel consumption, which is m dot F by P. Now, similarly, we can have ISFC, this is indicated specific fuel consumption, which is m dot F by P indicated power. We can have brake specific fuel consumption, which could be m dot F by Pb brake power. We could have frictional specific fuel consumption, which is m dot F by Pf frictional power. So, what we can then write this guy, the fuel conversion efficiency is like so eta F, which is a fuel conversion efficiency, we can write like 1 by, so this is m dot 1 by SFC into heating value. Okay. So, the specific fuel consumption is inversely proportional to the thermal efficiency of normal hydrocarbon fuel. Okay. Now, there are different range of fuels which can be used, and there are different values of kind of their efficiency level. Now, we will move to find out the other parameters like volumetric efficiency, so which is eta V. Now, volumetric efficiency is one used only in 4-stroke engines. So, this is used for 4-stroke which have a distinct induction process, and this gives a measure of the for the effectiveness of engine's induction process, as the intake system like the air filter, carburetor, intake manifold or intake valve, that restricts the amount of the intake, amount of the air inducted to the engine. So, this can be defined as that V dot A by Vs, which is the volume flow rate of the air into the intake system. So, this is volume flow rate of air into intake system to the, so this is a divided by the rate at which volume is displaced by piston. So, this one can write to m dot A rho A I V D N, where rho A I is the air density at inlet, V A is the rate of naturally aspirated induced air volume, Vs is the rate at which volume is displaced by piston. Since the piston speed is defined, so Sp is 2 Ln, where L is the stroke, then we can write eta V is 4 m dot A L by rho A I V D Sp, which is m dot A by rho A I V D. So, that is what this is a, where m is the mass of the air inducted into the cylinder per cycle. Okay. So, that is what we can. So, here we can write MA, and this is the mass of air inducted into cylinder per cycle. So, that is what you get the volumetric efficiency. Now, we can get propulsive efficiency. So, this is the piston engine is coupled to a propeller to furnish the forwarding thrust force. The propulsion efficiency also could be defined. So, now one can have some definition like engine, specific weight and specific volume of the engine, specific weight which is the engine weight divided by rated power, and you can have specific volume which is the engine volume divided by rated power. Relationship between these performance parameters we can establish. Now, we can write P is eta, let us say eta f m dot a n. So, this Q heating value fuel by air ratio divided by N R. So, which is eta f, eta v, N V d, Q heating value, rho A I, F by A by N R. So, now eta v is coming into the picture. So, rho A v eta. So, here the eta v, rho A I and d. So, this is the same M A one can use, that this is the M A is the mass of air inducted into the cylinder per cycle. So, then the torque, where we get eta f, eta v, v d, q h b, rho A I, f 2 pi n r, and mean effective pressure, that would be eta f, eta v, q h b, A I fuel air ratio. Now, the power per piston area often called specific power. So, the specific power is defined at P by A P, eta f, eta v in L, q h b, fuel by air ratio by n r, and introducing the mean piston speed, which S P bar is 2 L n, P by A P would be eta f, eta v by q h b, air fuel air ratio by 2 n r. So, typically for 4-stroke engine, this is P by A P is mean effective pressure S P by 4, and 2-stroke this P by AP is mean effective pressure SP by 2. So, these are the typical values of this power. And now we can move to some two-stroke engine or two-stroke Otto cycle engine. So, let us see some. This is a typical picture of two-stroke engine, where this is a two-stroke SI engine, what you can see, and this is the cycle, two-stroke Otto cycle. Now, what it talks about, that engine are very small, the two-stroke engine. This is used in ultra light aircraft similar to four-stroke engine. Also, this has some cylinder, piston, crankshaft, connecting rod. So, these are having all this. So, the petrol engine uses the spark plug, and the diesel engine replaces the spark plug with the fuel injector. Okay. And this is the typical cut section of the engine here, and this is the cycle of the engine. So, where you can see a fresh charge of fuel air mixture enters, and then you have like piston uncovers here, and then the uncovers the intake port while moving upward. Then there is already a fuel air mixture which is being compressed in the cylinder. So, which are head above the piston, and the top of the compression stroke, the explosion takes place due to the spark plug. Now, when the piston move downwards here in the third stroke, it slowly uncovers the exhaust port. Now, the exhaust flow takes place when the piston again moves back. So, this is shows you some of the idea about that these things. Now, we can compare some two-stroke and four-stroke engines, like simple comparison of, we can have, let us say, two-stroke and four-stroke. So, one could be the compression ratio. So, let us say here this is typically 18:1 to 100:1. This we are talking about compression ratio, and this case it is 10:1 to 20:1. Then speed, this case this is 2000 to 6000, then this is 400 to 3500, and then we can have power stroke. So, this is one working stroke per one revolution of the crankshaft. So, the one working stroke per one revolution of crankshaft, and this is one working stroke per two revolution of crankshaft. Okay. So, flywheel size, this is smaller, this is larger. Then you have construction this is simpler and easy to manufacture. This is complicated. Mechanical efficiency, this is higher due to few moving parts, this is lower. Thermal efficiency, this is small, this is quite high. Noise, this case it is high, this case also small. Fuel consumption, this case it is high, this case low. Finally, the maintenance, this is high maintenance, this is low maintenance. So, these are some of this comparison that you can think about. Now, with that we will go to now 4-stroke diesel engine discussion or the compression CI engine discussion. So, this is a compression ignition kind of reciprocating engine. So, this was first proposed by Rudolf Diesel in 1890s, that was very similar to the SI engine which was already discussed. So, here the air is compressed to a limit where then the fuel is injected and the combustion takes place. So, if we put the diagram for this again, like this is P and V diagram. So, that shot from 0 to 1, then it goes, it comes back 2, 3, 4, 5. So, this case is constant, this case is constant, and this is A, this is B. Similarly, if you put that thing back in T S diagram, so this is 1 5, then it goes up, comes down, comes here. This is 2, this is 3, 4, this is this is B, this is A. So, here P constant, here V constant. So, now here different process that we can define. Now, the thermodynamic process, like this case also 0 to 1 is constant pressure, induction of air at ambient pressure P naught. So, here the intake valve is open and the exhaust valve is closed, and now second 1 to 2, this is isentropic compression stroke. So, here the both the valves are closed. Then third 2 to 3, this is constant volume heat addition process. That means the combustion takes place here. So, here we get T3 is T max, P3 is P2, B2 is BTDC, specific heat Q in, which is Cp T3 minus T2, H3 minus H2, Q23 is Q in, which is m dot A Q HB combustion efficiency, m dot m Cp T3 minus T2. So, it can be m dot A plus f Cp into T3 minus T2. So, we can write Q heating value into eta C, so into Cp T3 minus T2. So, the specific work would be Q23 minus U3 minus U2, which is P2 V3 minus V2. Now, there is a cutoff ratio which is called beta here, that is defined at the V3 by V2, which is V3 by V2 T3 by T2. Okay. So, now we will go to process 3 to 4. This is again isentropic process, isentropic expansion stroke or the power stroke. All valves are closed. Then process 4 to 5, this is again constant volume heat rejection process. So, here the exhaust valve is open and intake valve is closed, and then we have 5 to 0, which is constant pressure exhaust stroke at P naught, which is ambient. So, now the piston then executes at an engine stroke in which the burned gases are purged into the cylinder through the open exhaust valve. So, the thermal efficiency that for diesel engine we can get W net by Q in, which is 1 minus Q out by Q in, which would be 1 minus Cb T4 minus T1 divided by Cp T3 minus T2. We can write 1 minus T4 minus T1 by gamma T3 minus T2. So, we can do little bit of rearrangement, and then what we can write, this could be 1 by Rc to the power gamma minus 1 beta to the power gamma minus 1 by gamma beta minus 1. So, where Rc is V max by V min, which is essentially V1 by V2 Cp by Cv, and beta is V3 by V2. So, this is what we get the thermal efficiency of the cycle, and we will stop here and continue the discussion in the next lecture.